In this example, the equation that we have right here looks a little bit different from the ones that we just did because we don't have this function of x and y here. Instead, we have this variable of z on the left-hand side of this equation. And the reason that we don't have this function of x and y in this example is because it's actually hidden from us. And here is how it's hidden. So let's take a look here. On the right-hand side of this equation, we have this x times exponential of 3x squared plus y squared. What you see right here is definitely a term that depends on the value of x and y, right? Which means that this term is also a function of x and y whose value depends on two inputs, x and y. In the end, this function value got assigned to this variable of z on the left-hand side of this equation. So don't be surprised that sometimes you don't see this function of x and y in your example because it can be assigned to a certain variable like z here. Okay, now let's take a look at what we need to find in this example. The first one that we need to find is the first order partial derivative of z with respect to x, which is going to mean the same thing as f with respect to x. And also we need to do that with respect to y as well, and same with f with the subscript of y. Now let's start with the first one, z with respect to x. As you know, when it comes to finding partial derivatives of a multivariable functions, all we need to do is to follow just one tip, which is if you work on a certain variable, you need to treat other variables as constant. For example, here we work with x variable, which means we are going to treat y as a constant. So let's make a quick note right here. Y is going to be treated as constant in this case. Alright, let's find out about this zx. Okay, z of x. But before that, let me write down the equation on the right hand side to make it a little bit bigger. Alright, z right here is going to be equal to x times exponential of 3x squared plus y squared. Alright, now I am going to differentiate this z with respect to x. So I focus on this x variable, which is right here and also here. So let's try to diff this one by one. So I'm going to start with the first one. I am going to diff this x with respect to x. Of course, I am going to get this 1 out of that. And then I'm going to differentiate this x right here, but as you can see, this x is inside an exponential. So I'm supposed to diff the exponential first. So as you know, diff exponential, you get the same exponential and everything stays the same. Alright, and as you can see, in the power of this exponential, we have some terms here. So in order to differentiate this correctly, you are supposed to apply the chain rule. You differentiate exponential and then you differentiate the power. So here I'm going to differentiate the power. And with respect to x, so I get 6x out of that first term. And then I am supposed to differentiate y squared with respect to x, but y is treated as constant, so I am going to get a 0 out of that. Okay, so here's what we got for the zx, z with respect to x. But I am sorry to tell you that what we just did was wrong. Okay, I just want to give you an example of how we can solve this incorrectly. Some of you might have noticed what went wrong along the way that we just did before, but some of you might have not, but that's okay. Let's see how this is wrong. What we just did is wrong. So let's make a note right here that what we just did is wrong. And here's why. Let's take a look at this. Z equal to all these terms. Alright. Okay, let me fix this line first. Okay. Let me make it a little bit bigger. Okay, what you see right here is a product of two terms with x inside. So let's take a look here if that makes sense to you. What you see right here is a product of two terms with x inside. The first term is this, right? This box with x inside, and this box is multiplied with this box right here with x inside. Alright, so it's like we have two sub-functions here, and both functions have x, and the first one we are going to call it u, and the other one we call it v, and here we have u dot v. And as you can see here, we have a product of two functions of x. If you want to differentiate that, you are supposed to apply the product rule. So make a big note right here that what we missed in the first place is the product rule. Need to apply product rule. Okay, so let's use that. I'm pretty sure that most of you know how to use the product rule, which is the u dv plus v du. So u dv, right here we are working with the partial derivative, so we are going to use the partial diff right here. dv has to be partial diff with respect to, of course, x in this case, and plus v du, and of course this has to be partial, du by dx. So let me write down v and u again. U here is going to be equal to just x, and v here is going to be equal to exponential of 3x squared plus y squared. Now we have this product rule right here, so we can proceed to perform the calculation. U right here is equal to x, and then I need to diff this v with respect to x. So of course exponential right here is going to stay the same. Alright, the power stays the same. But after that, I am supposed to apply the chain rule to these terms. Alright, I am supposed to diff that with respect to x, and I get 6x. And for y, it's going to go away. So I can close it right here. Now, plus v, okay, the whole term, I bring it right here, 3x squared plus y squared. Now I need to diff u right here with respect to x. Of course, I get this 1. Now you can complete all these terms to make it look a little bit nicer. So you have this 6x squared, e to the power of 3x squared plus y squared, plus e to the power of 3x squared plus y squared. Right? You can take the common term and make it to look like this, e to the power of 3x squared plus y squared, and with the parenthesis of 6x squared plus 1. Alright, either one is fine. And here is how you perform the calculation correctly for zx. Alright, do not forget about this product rule. Now let's try one for the zy. Alright, now okay, let me change. Okay, zy right here, zy. Okay, right now we are working with y variable, which means that we are going to treat x as a constant. Okay, treat x as a constant. The question is, do we need to apply the product rule again? I don't know. Let's take a look here. Z, let's write it down again. Z equal to x e to the power of 3x squared plus y squared. As you can see, here we are working with y, and there is just one y right here, right? So y is not at the front like x that we just did. So here we don't need to apply the product rule because we only have one y right here. So we just need to differentiate this with respect to y normally. So here, let's apply that. X is going to get treated as constant, so nothing changes here. And exponential stays the same, 3x squared plus y squared. But then we are supposed to apply the chain rule to these terms with respect to y. And in this case, I am going to get this 2y out of that. Alright, now let's put everything together. We have this 2xy exponential of 3x squared plus y squared. By the way, let me make a comment right here that 2y here comes from chain. And also 6x here comes from chain. Okay? Now, okay, so we have this final answer for z with respect to y. Alright, so let's move to the next example, number 4. Okay, let's take a look at this number 4 here. Once again, we have this z equal to some terms, and of course these terms. these terms depends on x and y. So this is definitely a function of x and y, and we have this relation between this function and z right here. Alright, so we are supposed to find the first derivative, partial derivative with respect to x and also with respect to y. Now let's do that really quickly for this one. Z with respect to x first, and of course in this case we are going to treat y as constant. Alright, now I am going to take a look at this equation again to know the places of x variable. So we have cosine of xy and we have this ln of xy squared. Okay, where are the x's? One is right here and the other one is right here. As you can see here, I see two terms of x multiplied together. In other words, I see a product of two subfunctions of x. One is this subfunction, the first one at the front, okay, and the other one is right here. Each of these has x in it. So this one I'm going to call it u and this one is v. So let me write it down again. U equal to cosine of xy, has x in it, and v here has is equal to ln of xy squared, also has x in it. Okay, I am going to proceed on this, and definitely I need to use the product rule. Okay, so product rule, u, okay, change color to blue, u dv by dx plus v du by dx. And make a note right here that we need to apply the product rule. Product rule. Okay, so let's work on that. U has to come here and u equal to cosine of x and y. Alright, and then I am supposed to find dv by dx. So I look at this one. Differentiate this with respect to x. Since x is inside ln, right here, x inside ln, I am supposed to diff ln first. So I am going to get 1 over xy squared. Alright, and then I apply the chain rule. I diff the inside with respect to x, and I get y squared out of that. Alright, y squared. So let's make a note right here that y squared comes from the chain. Alright, now let's move further. V right here. Okay, I run out of space, so let me change this. Okay, I'm sorry about that. V equal to ln of xy squared. Alright, this is better. So I'm going to bring v right here. It's going to be equal to ln xy squared. Alright. And now I need to differentiate du with respect to x. Alright, differentiate u with respect to x right here and diff this. And as you can see, x is inside, so you are supposed to diff cosine first, and that's how you get minus sine, and you keep the inside alone. Alright, and after that you can perform the chain rule to diff the inside of this cosine with respect to x, and that's when you get this y out of that. Alright, so y right here comes from chain. Alright, and you can make a note right here. This is this came from ln, and this came from cosine. Alright, now this looks a little bit messy, so work out the numbers to make it a little bit cleaner. As you can see here, y squared right here can cancel with that, so in the end you have this 1 over x. Alright, cosine of x and y. Cosine of x and y plus, okay, we have lots of terms here. Definitely we have this minus sign, so I'm going to bring it to the front. So this plus sign becomes minus, right? Minus y sine of x and y, okay, and ln of xy squared. Okay, and that is the answer for z with respect to x Alright, let's move to z with respect to y. As you know, z with respect to y, we are going to treat x as a constant. Now we need to look at the z, the expression for z again, to determine whether we need to apply the product rule or other kinds of rules. So we have this z right here again equal to cosine of xy and times ln of xy. Oh, sorry, this is supposed to be ln of xy squared. We have y right here with the cosine and y right here at the ln again. So definitely this is two terms of y in it, and they are multiplied together, so we have a product of u and v. So definitely we need to apply the product rule. U equal to cosine of xy and v equal to ln of xy squared. Alright, definitely need a product rule here. So here it's going to be u dv, but this time it's going to be with respect to y, right? So pay attention to this. This is supposed to be dv with respect to y, plus v du, and this time with respect to y. So make a note right here, product rule. And it's nice to have this comment right here with respect to y, and above here with respect to x. Okay, so let's work on this. U has to come here, so u equal to cosine of xy. And then I need to perform the differentiation of v with respect to y, so I'm going to look at this and diff that with respect to y. Of course, I need to diff ln first, so I'm going to get this out of that. 1 over xy squared, and this came from ln. Alright, and then after that I'm supposed to diff the inside of this with respect to y, and I'm going to get 2xy out of that. So diff y squared, I get 2y with the x, it becomes 2xy. Alright, now next term we have this v, so let's bring everything here. V ln of xy squared multiplied with the du by dy. Alright, so I'm going to look at this and diff this with respect to y. Of course, I need to diff cosine first. It's going to come out to be minus sine xy, just like before. And then I need to diff the inside with respect to y. And that's how I get x out of that. Okay, now let's make a note along the way that this came from chain, this came from cosine, and this came from chain. Okay, let's cancel some terms right here. Y with this square here with this y, and x here with this x. So here we have 2 over y left. 2 over y cosine of x and y. Then we have this minus sign. Let's take it to the front, and then we have this x and sine of x and y, and of course we have this ln of xy squared. Alright, and that is the answer for this example, both for zx and zy. Alright, here don't forget that we need to perform the product rules for both x and y in this example, which is different from number 3. Number 3 we only need to apply for just one, so it depends on the form of your function. Alright, so pay attention to the form. Now let's move to example number 5 in the next slide. The first thing I'm going to point out in this example is about the variable z. So let's take a look at z right here. As you can see, this z right here is inside the parenthesis, which means that z right here has become an input to this function. This function, as you can see, has 3 inputs. Number 1 is x, number 2 is y, and number 3 is z. So make a note right here to remind ourselves that z right here is an independent variable. Independent, or you can call it input variable. And this is different from the ones that we have seen in example 4 and 3. Let's take a look at example 4. So in example 4 we have z as well, but it's on a different side of the equation. It's on the left hand side, and it takes the value of the function. Even though they have the same symbol, this z right here is an input, and it's the one that changed the value of the function. So it does different things. Alright? So I know that this is an obvious difference, but every single year some of you are going to get confused about the difference between the two. So I need to mention about this. Now let's get back to this example. So what do we need to find here? We need to find all the first order partial derivatives, all the first order, and then we need to find the second order, which is this one, second order, and then the third order. We have x, y, z right here, third order. Same here with this z, x, y, third order. So let's talk about the first order partial derivatives here. Since we have 3 inputs, it means that we can take the partial derivatives with respect to each one of them. And this means that we have 3 of them here. The first is f with respect to x, then with respect to the next variable, which is y, and then the last one, f with respect to z. Okay, lots of things to do. Like, we have 6 values here. So let's start with the first one. So let's start with this fx, f of x. So we are supposed to find the partial derivative of f with respect to x. And just use the same tip as we used before. We treat other variables as constants. Since we work with x right here, we are going to treat y and z to be constant. So make a note right here, y and z as constants. Alright, so all I need to do here is to look for x inside this function, and I see only 1 right here and nothing inside this sign, so that's good, which means that I can just diff this x squared right here, and then I get this 2x out of that. I diff 2z with respect to x, I get 0. Alright, and the back term right here doesn't have x in there, but this is multiplied into the front term, which means that I need to keep it. So this is sine y cubed z. Keep in mind that if a constant is not alone, then you need to keep it. But if the constant is just on by itself, then you can just differentiate that into 0. So here we get the answer for this first value, which is 2x times sine y squared, y cubed z. There you go. Very quickly we found the first one. Let's move to the second one, which is the function partial derivative of f with respect to y. So next one is going to be fy, and since we are working with y here, x and z has to be treated as a constant. So x and z as constant. Alright, same tip for 5 examples already, but that's good, right? Keep it simple. Now I need to take a look at the function again and look for y in this function, and I see just one place with y, which is right here inside sine. So let's perform the differentiation on that. The rest need to be treated as constants, so the front term stays the same, x squared plus 2z. And since y is inside the sine, I need to diff sine first, so I get cosine, and the terms inside I keep it the same. Alright, y cubed z, and then I need to apply the chain rule to the term inside, right? So I need to apply chain rule. I need to diff that with respect to y, and of course I get this 3y squared and z right here. So make a note right here, this came from sine, alright, and this came from chain. Okay, so in the end I have this term which is equal to all these, x squared plus 2z times 3y squared z times cosine of y cubed z. And that is the answer for the second first order partial derivative with respect to y. Now let's move to the last one, the last for the first order, which is f with respect to z. And as you know, we are working with z variable, which means we are going to treat the others to be constants, and they are y, x and y as constants. All right, so need to find that. I need to go back to the function and look for z inside this function, and I see two places. Well, when you see two places, there is a chance that it might get tricky. So I see z right here and z right here. Z in front right here, and so I have this chunk in the front and another chunk in the back. So what we are looking at here is a product of two sub-functions with z inside. So the first term right here, the first chunk right here has z in it, and then it's multiplied with another chunk at the back with z in it. So we are looking at two sub-functions, and I'm going to call the first one u right here, and the second one is v. Right, to save some space, I'm going to do this. U equal to x squared plus 2z, and v right here equal to sine of y cubed z. Alright, since we have two of them and they are multiplied together, so we have to apply the product rule. So make a note right here that for this case we need to apply product rule. Okay, so it's going to be equal to u dv, and since we are working with z variable, it's supposed to be dv by dz, dv by dz plus v du by dz again, and that's going to be equal to, I'm going to work with this u, I'm going to take the whole thing here, and it's going to be equal to x squared plus 2z. Alright, now I need to find this dv by dz. So I need to look into this v and differentiate this with respect to z, and z is right here in the sine, in the function of sine. So I need to diff sine first to get cosine. Alright, and I keep everything inside the same before I perform the chain rule to the inside. Diff that with respect to z, I get y cubed out of that. Alright, now plus v du. Now v, I take the whole thing here, v is sine y cubed z. Alright, and then I need to find this du by dz. So I need to look at this and differentiate this with respect to z. And this one is easy because I get 2 out of that. Okay, so I get 2 out of that, du by dz. So let's work out these terms to make it look better. So here I have this y cubed with this times with the x squared plus 2z. Alright, and then I have this cosine of y cubed z plus 2 sine of y cubed z. And there you go. That's the last first order partial derivative that we need to find, f with respect to z. Okay, that's a lot of things, right? We still have 3 more to do. So let's try the fourth one, which is the second order partial derivative with respect to x first and then to y. Alright, take a look here. We know the order. X has to happen first and then y later, which means that in order to find this f of with respect to x and y, okay, we are supposed to differentiate fx with respect to y. Alright, let's do that. So since we are working with this fx and we need to diff this with respect to y, we are going to focus on this fx right here and going to use it. So we have this fx and we are going to differentiate this with respect to y. And looking at this, I only see y right here inside this function of sine. So let's diff this. Okay, Now 2x stays the same, and then I need to diff sine function to get cosine, and I keep the inside the same, y cubed z. Alright, and then I need to perform chain rule inside, so I need to diff that with respect to y, and then I get 3y squared z. Alright, so make a note right here that this comes from sine, alright, and this comes from chain. So in the end I have this value of 6xy squared, and with z right here times with the cosine of y cubed z. Alright, and that is the answer for the second order partial derivative of f with respect to x first and then y. Okay, now, oh, by the way, I need to put this came from sine, just in case you want to know where it came from. This came from sine, right, and this from chain, right, this from sine, this from cosine, and this from chain. Oh, I'm sorry, not for this one. Okay, now let's move to fxyz for the next one. Right, that's going to be the third order partial derivative. F with respect to x first, and then y, and then z. Which means that we are going to need to differentiate f of xy with respect to z. And we need this expression f of xy, and we have it right here. F with respect to x and y, we can use it and differentiate that with respect to z. So let's try this. We are going to differentiate this with z, with respect to z. So I need to find out where the z are. So we see some z right here, the first one, and then the next one is right here at the back. So as you can see here, we have two places for z. And by the look of this, we see two terms that has z in it, and they are multiplied together. In other words, we have a product of two subfunctions. Products of these two, and each of these has z in it. So this has become u, and this has become v. So let's make a note here that for this case, u is going to be equal to 6xy squared z, and v equal to cosine of y cubed z. Alright, since we have a product of two terms, we are supposed to apply the product rule here. Apply product rule. Okay, so this is supposed to be u dv by, well, we are working with z right here, so dv by dz, plus v du, du by dz again. Alright, so let's find them. U here is supposed to be equal to 6x y squared z right here, so I take it to here, 6x y squared z. Multiply with dv by dz. So let's find out about this. So I'm going to look into this v and differentiate this with respect to z. So here I have this, I need to diff cosine first, so I get minus sine, and then I keep the terms inside the same, y cubed z. After that, I need to diff the inside of this with respect to z, and I get y cubed. Alright, y cubed right here. Make a note that this comes from cosine, right? And this comes from chain. Okay, now next term, we have v du. Let's take v here. V here, we have cosine of y cubed z. And then we are supposed to find this du by dz. So let's take a look at u right here and diff this with respect to z. Z is just here, so when we diff this, we only get the constant out of that. So constant is going to be 6xy squared, and z right here becomes 1. Alrighty, so many terms. So let's make it cleaner here. So let's combine them. We have this minus 6x y to the power of, we have 2 right here and 3 right here. It has become 5. And z still there, and then we have this sign with the inside of y cubed z. Alright, plus here we have 6xy squared, cosine of y cubed and z. And that is the answer for the third order partial derivative of f with respect to x first, then y, and then z. Alright, now last one. Let's move to this last one. Also a third order partial derivative, which is f with respect to z first, and then y, and then x, equal to what? Alright, now let's make a note right here. In order to find this, we are supposed to differentiate this function with respect to z first, and then to y, and then to x. So make a note right here to find this directly. Need to find, alright, first fz, and then fzy, and then fzyx in order. But if you can remember what we talked about in the previous example, we talked about the order of the operation of the partial derivative, that the order doesn't matter. If you can recall, fxy equal to fyx. What I told you there is that the order of the operation doesn't really matter as long as the number of the operation on each variable is the same. Alright, as long as the derivative with respect to x is just 1 and 1 right here the same, and y just 1 and 1 right here the same, the final values are going to come out to be equal. So make a note right here that order of operation doesn't matter. Order of operation, and when I talk about operation here, I mean the differentiation. Well, we can put order of differentiation, right? Diff doesn't matter. Doesn't matter, okay? So we can take a look at this fzyx that we need to find. This function that we need to find has the differentiation with z once, y once, and x once. Right? Same with what we just did. This previous one, x once, y once, and z once, which means that this value that we need to find, fzyx, is going to be equal to f of xyz. F of z with respect to z, y, and x is going to be equal to f of x with respect to x, y, and z. Alright, as long as the number of diff on each variable is the same, which is just 1 in this case, the final values are the same. Alright, so let's make a box around here, but keep in mind that this is not the only relation between them. This is also equal to f of zxy. Oh, I am sorry. They ask for this zxy, right? So let me change this. I am sorry about this. This is supposed to be x first and then y. Zx and y. Alright? Which means that I need to change here as well. This z and then x, zx and zxy. Right? Really sorry about that. Zx here and zxy. Alright? Which means that the value that we want right here is supposed to be zxy. Okay. And it's going to be equal to the xyz that we found earlier. But I want to add you right here, add this to you. So the relation is not just these two. This is also equal to f of z yx also equal to f of x, z, y, which is also equal to f of y, z, x, equal to f of y, x, z. All of them have to be equal because each one of these has the same amount of differentiation on each variable. And as you can see here, we only perform diff once on each variable, and they have to be equal.